All right, in this last video in section 14.6, we're going to look at question 8 that says, consider the solid E given in spherical coordinates rho phi theta, where rho varies from a to 1, phi varies from 0 to pi over 2, and theta varies from 0 to 2 pi. Our job is to find the centroid of the solid E using spherical coordinates, making an appeal to symmetry where appropriate. Then it says, note that your answer will depend on A. And finally, for what value of A will the centroid lie on the boundary of the solid E? Okay, so I've gone ahead and sketched these two spheres, radius A and radius 1. And since our angle phi varies from 0, that's when we're on the positive z-axis, to pi over 2 when we're in the xy plane, and theta varies from 0 to 2 pi, we're then looking at the region bounded by these two spheres and above the xy plane. And since we're looking to find the centroid of this solid, we have uniform density, and I'll call that density function delta, just to not confuse it with rho, the radial distance in spherical coordinates. Okay, so delta here is equal to this constant k. And also notice by symmetry, since our region is symmetric with respect to the z-axis, we can conclude that the x and y coordinates of our centroid will be 0. So in other words, the centroid will lie on the z-axis. Okay, so that's really nice. Cuts down on a lot of our calculation here. Okay, so let's go ahead now and compute the mass. So I'm going to compute the integral of our density function, delta, over our solid. And since delta is just a constant, integrating a constant over this solid is just going to give us that constant k times the volume of the solid. And we're just looking at this volume between two half spheres. And so I can just use the fact that a volume of a half sphere is 2/3 pi r cubed to get this expression k times 2 pi over 3 times the quantity 1 minus a cubed for the mass of our solid. Okay, so now let's go ahead and look at computing the moment. And since we know x and y bar are 0, we really just need z bar. And so we really now need to compute just the xy moment. So, okay, we have our bounds here for rho, phi, and theta. And the xy moment is going to be the integral of z times our density function over our solid E. Now z in spherical coordinates is rho cosine phi. Our density is k. And our dv, our volume element in spherical, recall, is rho squared sine phi. Okay, and then we're integrating here in the order d rho, d phi, d theta. And we have our appropriate bounds there. All right, now I've gone ahead and split this integral up because we have, well, a product of something that depends only on phi, which is just the sine phi cos phi. So that's this phi integral here in the middle. Then we have this rho cubed, okay, and that's peeled off over here. Then we have the theta integral, and the integrand is totally independent of theta, so that's just going to give us this integral 0 to 2 pi of d theta, and then I just put the constant out in front. And these are all pretty straightforward integrals. This phi integral, you may want to integrate with a substitution. You could set just u to sine phi. But in any event, you're going to wind up getting k times pi over 4 times the quantity 1 minus a to the 4th for this xy moment. And so then z bar, the z coordinate of our centroid, will be the xy moment divided by the mass. So I'm just going to divide these two quantities we've now computed, and you get this expression 3/8 times the quantity 1 minus a to the 4th all over 1 minus a cubed. So putting that all together now, we can conclude that the centroid is located at 0, 0, and then 3/8 times this 1 minus a to the 4th all over 1 minus a cubed. Okay, so finally, when will the centroid lie on the boundary of our solid? Okay, well, for that, we would want the z-coordinate of our centroid to equal this inner radius. Okay, so in other words, we want this expression to equal a. So if I set that equal to A, this is a rather complicated equation. It's a degree 4 equation, so I've just used Desmos here to get an approximation. So I have a sketch here in black of this curve, 3/8 times this messy expression, and then I have just y equals x, because I'm setting this expression in terms of a equal to a itself, and I can see that they intersect at about 0.389 there. Okay, so that value of a would imply that our centroid would lie on the boundary of our solid. Now notice if you do say, well, what if a were equal to 1? So in other words, you really wouldn't have any volume at all. Now, if you go ahead and just set this expression equal to 1, you'll find that there is a solution at about 2.57. Again, I just used Desmos to find that. But if we're actually going to have a solid here, just based on the definition of the solid E here, A does need to be less than or equal to 1. Okay, so that's going to do it, and I will see you next time.